Matrix A is of size m by n. Matrix B is of size n by q. We are interested in the rank of the product AB, which is a matrix of size m by q. The claim is that rank of AB is the rank of matrix B minus the dimension of this subspace, the intersection of the null space of A and the range or column space of B. What is the motivation behind this term here? Note that when we multiply matrix B from the left by matrix A, what we are doing is that we are applying A to the columns of B. And so the matrix product is basically every column in B multiplied from the left by matrix A. And so it makes sense that we are interested in what vectors live in the column space of B that are also in the null space of A. So for example, suppose that, so this is like a special case. If the range of B is totally contained in the null space of A, this means that every column in B is in the null space of A. So when you multiply AB, then every one of those columns will be 0, and AB will be an all 0 matrix. And a matrix has a rank 0 if and only if it's the all 0 matrix. Now, let's look at the right-hand side. Under this situation in which the range of B is fully contained in the null space of A, the intersection is the range of B. And the dimension of the range of B is the rank of B. Rank of B minus the rank of B will give 0, which is what we expect. That the rank of AB, if it happens that every vector in the column space of B lives in the null space of A, then this product is the all 0 matrix, and it is indeed a matrix of rank 0. Okay. Now, the other special case is, what if this intersection is just the all 0 vector? Okay, the n-dimensional all 0 vector. Okay, so in that case, whenever you multiply A by a column of B, you get a 0 if and only if the column in B is the all 0 vector. Otherwise, you do not get a column that is all 0. In this case, we expect that the rank of the product is the rank of B itself. And, in this case, yes, this will be true from the formula because the intersection is just one point, which is the all 0 vector, and the dimension of this subspace is 0, and rank of AB will be equal to rank of B. So again, it seems, again, from if we understand the product A times B as A acting on the columns of B, it really seems that it is important to take into account the intersection between the column space or the range of matrix B and how it is related to the null space of A, the set of all vectors that, that A times any of those vectors will give basically the all 0 vector. Now, assume that the dimensionality here of the null space of A intersection the rank of B, the range of B is equal to S. So suppose that this subspace, it has a dimension that is S. Suppose that this subspace is spanned by this basis, this set of vectors x1, x2, all the way to xs. We need S vectors because we are assuming that the dimensionality of the null space of A intersection the range of A to be, the dimensionality is S, and so we need S vectors in the basis for this subspace. Of course, the null space of A intersection the range of B is contained in the range of B. It is also contained in the null space of A. Now, let the rank of B, which is the dimension of the range of B, be S plus T. So it is this S plus T, okay? Because note that the range of B is the range of B intersection, and then we have the null space of A union the complement of the null space of A. And so the range of B can be written as the union of two disjoint subspaces, range of B intersection null space of A, union the range of B intersection the complement of the null space of A. Okay, so what we are doing here is that the dimensionality of this, we took it as S, and so the remaining part, we took the dimensionality to be T, and the sum of these two guys, these are subspaces that, whose only intersection is the all zero vector, then the dimensionality of the range of B is S plus T. So let's extend those basis vectors so that we can span the column space of B. So now we will have the vectors from x1 to xs. So those are a basis for the null space of A intersection the range of B. And those are T basis vectors to span the subspace which is the range of B intersection the complement of the null space of A. So now the important vectors are those ones. AZ1, see those guys, Z1 all the way to ZT, AZ1, AZ2, and all the way to AZT. So those are the important vectors. Again, when we multiply A by B, we can understand it in a number of ways. And what is relevant for us is this way of understanding or visualizing what is going on. It's as if we are applying matrix A to each column in B. So now we will apply matrix A to every one of those basis vectors here. Those are the basis vectors that span the range of B intersection the complement of the null space of A. Now our first claim will be that those vectors, so claim, those vectors AZ1 all the way to AZT, they span the range or column space of the product AB. How can we show this? Take an arbitrary vector, small b, in the range of the product. B is in the range. So there must exist a vector y such that B can be written as matrix AB times y. So that's the meaning that B is in the range of AB. It can be written as a linear combination of the columns of the product AB. Or we can write down B as the matrix AB multiplied by a vector of size q by 1. And if we say that B is in the range, this vector must exist such that AB times this vector, here we call it y, is equal to B. Note that by is in the range of B by definition, because by is equal to y1 times the first column of B plus y2, that's the second component in vector y, times the second column in B, all the way to the qth component in y and the qth column of B. It's a linear combination of the columns. So by is in the range of B. Because it's in the range of B, now we have a basis for the range of B. So we can write by as a linear combination of those vectors, the x's and the z's, like this. Now, if we multiply both sides here by matrix A, then we will get ABY, which is vector small b, and we just apply, using linearity, A multiplied by this sum will be the sum of those scalars alpha I times AXI, and we will do the same in the second sum. Okay, so we started with the vector in the range of AB. So the vector can be written as AB times some vector y. By is a vector in the range of B, so it can be written as a linear combination of the vectors from x1 to xs and z1 to zt. Vector small b is A times this vector, so we just multiplied by A, and this is our vector B, which is a vector living in the column space of the product AB. Don't forget that the x's are a basis for the intersection between the null space of A and the range of B. So this thing is contained in the range of B. It is contained also in the null space of A. So this means that A multiplied by any x vector, x1 or x2 all the way to xs, is basically an all zero vector. So AXI is equal to the m-dimensional zero vector, because those vectors are in the null space of A. So vector B now can be written, as this summation with the vectors AZ. So vector B is this. Vector B is any arbitrary vector chosen from the range of AB. Now we can write vector B as a linear combination of those specific vectors, AZ1, AZ2, all the way to AZT. So indeed, this set of vectors spans the column space of the product AB, because any vector in this range of AB can be written as a linear combination of those columns, or those vectors AZ1 to AZT. So we have the spanning property. Does this mean that those vectors are like a basis for the column space of AB? Not yet. We need now to show that they are linearly independent. So now we have shown that they span the range of AB. If moreover we show that they are linearly independent, then they are like a basis for the range of AB, and then the dimensionality of the range of AB, which is the rank of AB, will be equal to T. Okay, so we still have to do this step. So consider this equation. I will take those guys and form a linear combination of them and ask the question, if I construct a linear combination of AZ1, AZ2, all the way to AZT, and equate that linear combination to the all zero vector in the m-dimensional space. Don't forget that A is m by n, and Z is are vectors of n of size n by 1. Then the vectors AZ1, AZ2, and so on are linearly independent if the only possibility for this equation is to have all those scalars equal to 0. So we'll start by writing down this equation, and then we can take A as a common factor. So A times this linear combination of vectors Z1 all the way to ZT is equal to the all zero vector in m dimensions. A matrix times a vector is all zero. It means that this vector is living in the null space of A. And because it's living in the null space of A, okay, so it is living in the null space of A. And also note that those Z vectors here are part of the basis for the range of B. So a linear combination of Z1 all the way to ZT is in the range of B. So we have two things. That this linear combination, because of this equation, this linear combination is in the null space of A. Moreover, this linear combination, because it's a linear combination of the Z vectors, then it is also in the range of B. So this linear combination is in the intersection of the null space of A and the range of B, which means that this linear combination can be written using the basis set for null space of A intersection range of B. Those are the X vectors. So because this vector is in the null space of A and is in the range of B, then again, it can, this vector is a linear combination of the X's by definition, because those X vectors are basically a basis vector for this particular subspace. We can move this summation to the other side, and now we have, this is our equation. We have a linear combination of vectors Z1 all the way to ZT, and another linear combination for involving the vectors x1, x2 to xs. This linear combination is equal to the all zero vector in n dimensions. But the x's and z's, here is by construction, basically this set omega containing those vectors is a basis. And so those vectors are linearly independent. And so the only possible way we can make this summation equal to the all zero vector is for all the etas and all the gammas to be equal to 0. So if we go back here, if there is a linear combination of vectors az1, az2 that is equal to the m-dimensional all zero vector, it must be the case that the gammas are equal to 0, all of them. And so those vectors az1 all the way to AZT, they are linearly independent. So they are linearly independent. And they span the range of the matrix product A times B. And so they are a basis for the range of the product AB. And so how many vectors do we have? T vectors. So T is the rank of AB. T is the rank of AB, and that's it. So now we have the rank of AB is equal to T, which is equal to T plus S minus T. T plus S is the rank of B. And the T, from the very beginning, T is the dimension of the null space of A intersection the range of B. And so this is the proof of this result here. Very important result. Now we can build on this result. And for example, the rank of AB is less than or equal to the rank of B, right? Because this dimension is something that is non-negative. And so it must be the case that the rank of the product AB is less than or equal to the rank of B itself. Okay, so this is an inequality that we can obtain. Note, of course, that the rank of B itself is less than the minimum of the two dimensions of B. So B is an n by q matrix, so the rank of B is upper bounded by the minimum of these two numbers. We expect also that the rank of AB should be less than the rank of A. Is this true? Yes, it is true. So let's take for granted that the rank of the matrix is exactly equal to the rank of its transpose. So the rank of AB, this should be equal to, the rank of AB is exactly equal to the rank of the transpose of AB. Now, AB all transpose is B transpose A transpose. Now, apply our result from here. The rank of a matrix times a matrix is less than or equal to this matrix on the right. So the rank of B transpose A transpose is less than or equal to the rank of the matrix on the right, which is the rank of A transpose. And now we are taking for granted that the rank of A transpose is exactly equal to the rank of A. So now we have the rank of AB is also less than or equal to the rank of A. And so the rank of AB is less than or equal to the minimum of the rank of A and rank of B. So this is a nice result. The rank of the product of two matrices is upper bounded by the minimum of the two ranks. We can say more. Let's basically try to find a lower bound on the rank of the product. Null space of A intersection the range of B is contained in the null space of A. It's also contained in the range of B, but what will be useful to us now is to take it to be contained in the null space of A. So the dimension of this subspace is less than or equal to the dimension of the null space of A. Now, from the rank nullity theorem, it tells you the following, that the dimension of the range of A, so this is the rank of A, plus the dimension of the null space of A, this should be equal to the number of columns of matrix A. Matrix A is of size m by n, so this summation here is equal to small n, which means that the dimension of the null space can be written as small n, which is the number of columns in matrix A and the number of rows in matrix B minus the rank of A. Just move this to the other side. So by applying the rank nullity theorem, now we have that the dimension of null space of A intersection range of B is less than or equal to n minus the rank of A. But we proved a result. We proved that the rank of AB is equal to the rank of B minus the dimension of this subspace. So minus the rank of AB is the dimension of the null space of A intersection the range of B minus the rank of B. So this is our previous result, just multiplied, just with the two sides multiplied by -1. So now the dimension of the null space of A intersection the range of B minus the rank of B is less than or equal to n minus the rank of A minus the rank of B. So basically, we used this inequality after subtracting the rank of B from both sides. So we have now this inequality, multiply both sides by -1, and of course this will require that we change the direction here. And so the rank of the product AB is greater than or equal to -n plus the rank of A plus the rank of B. So that's a nice result. So now we have a lower bound on the rank of the product. Okay, so now we have this, that the rank of the product of two matrices AB, okay, and the sizes, this guy is m by n, and this guy is n by q. Okay, and so we know that the rank of A is always less than or equal to the minimum of the two sizes m and n, and the rank of B is less than or equal to the minimum of n and q. Now we have the rank of the product is upper bounded by the minimum of the two ranks of A and B. And the rank of AB is lower bounded by the sum of the two ranks minus n, which is the number of columns of A or the number of rows of B. If the rank of B is equal to n, if the rank of B, so suppose that we are in a case in which the rank of B is equal to n. So of course, you know, a necessary condition for this to be true is that Q is greater than or equal to n. In this case, if the rank of B is n, then this left-hand side becomes rank of A plus n minus n. So it becomes the rank of A. So the rank of A is a lower bound on the rank of the product. Now, if the rank of B is equal to n, note that the rank of A is less than or equal to the minimum of M and N. So this minimum is less than or equal to M, and it is also less than or equal to N. Okay, so it must be the case that the minimum here will be the rank, you know, between these two terms. The rank of B is N, the rank of A is less than or equal to N, and so the minimum of the two ranks is actually the rank of A. So we have the rank of AB living between the rank of A and the rank of B, the rank of A. So it must be the case that if it happens that the rank of B is exactly equal to n, the number of rows of matrix B, then in this case, the rank of AB is equal to the rank